Hi, I'm Mark. Today we're going to talk about a recent talk at the Perimeter Institute. This talk was given by Dr. Flip Tanedo. In a side note, for those of you participating in the You Can Solve Nature series who are trying to solve nature on your own with minimal clues, I think that's wonderful. This particular video will have some advanced concepts in it, so if you're on the You Can Solve Nature track, you might want to not see the spoilers in this one at this point. Keep going on your track. I think you'll find it very rewarding to discover nature on yourself with a few clues. This is the cover slide from that lecture. I've gone through the lecture and clipped out all the non-technical parts because I would like to focus on the message here about dark matter. Flip titles this A Theorist's Apology. I found it to be more than an apology. It's more nuanced. I found it to be part confession, part frustration, part heartbreak, part wisdom, with a large dose of renewed commitment. In saying that now, it reminds me of the stages of grief as proposed by psychiatrist Elizabeth Kubler-Ross. And the 5 stages of grief are denial, anger, bargaining, depression, and acceptance. And as you watch Flip's lecture, you'll see how he goes through these stages from the time when he did his thesis, looking for particles that would implement the Higgs, all the way through to trying to match up to dark matter measurements and trying different models that might help do that, to eventually kind of realizing each of those had its own problems, not really making a lot of theoretical math-based progress, and sort of a resignation to rededicate himself as a dark matter theorist. So that's all very interesting. As we go through this talk, I will pause occasionally and make comments about what Flip has said, because from my point of view, from the next era of science, where we really truly get to the fundamentals of nature, things look quite a bit different than what is being said by the dark matter people and the particle physics people in academia. And it looks different because there's a new solution to nature. It's always been there. It was just not found. The opportunity to find it presented itself in 1900 and during the whole classical to quantum transition. But due to the circumstances and perhaps a lack of creativity on the part of scientists at the time, they didn't find this architecture of nature. So if we go back in history to around 1900, apply some more creativity, we discover a new architecture of nature that is very parsimonious, fairly easy to reason about logically, really reasonable to visualize, especially with the help of animation, and I'll show you some of those. And the questions that Flip and the cosmologists are trying to answer become rather self-evident. So I'll show you the architecture. I kind of call it an eigenarchitecture. I may not have everything visualized exactly perfectly, but I think it will show you in the way I describe it the hypothesis of how assemblies of point charges form and make the particles in the standard model and make space-time. It's very fascinating. I'd love to show that to you.
Please join me in welcoming to the stage Professor Flip Tanedo.
My name is Flip. I am a theoretical physicist, and I work on dark matter. Here's a false color illustration of dark matter. Our bubble of dark matter is actually sitting in a cluster of bubbles. If you looked into each of these bubbles, most of them also happen to have galaxies sitting there. And this is our cosmic mystery. Start with the assumption that dark matter exists, and there's one thing that we know pretty well, which is roughly how much there is. We are about 15%, and most of the rest of it is dark matter. And the evidence comes from the sky. When we look at the motion of stars in galaxies, when we look at motions of clusters of galaxies, and when we look at the photons from the cosmic microwave backgrounds, the very first photons from 13 billion years ago reaching our telescopes today, each of these probes give indelible evidence that there is stuff that is clumped up that cannot be explained by protons, neutrons, and electrons and their cousins. But here are 12 pieces of evidence for why we are so sure that dark matter exists. What all of these different pieces of evidence are telling you, taken at different length scales, at different times in the cosmic history, the most conservative thing we can say is that all of these different pieces of evidence are pointing to something that looks like matter that is not the stuff that we are used to. All of this evidence is coming from the sky. I am a theoretical particle physicist. The problem is, what is this dark matter? And this is a history of two tribes: particle physics, where the problem is, and astronomy, where the observations are.
I found it refreshing here that Flip is honest enough to admit that the problem lies in particle physics. He's absolutely correct. And the reason the problem lies there is because quantum theory is an effective theory. It has no basis in nature. Like general relativity, it has math that works very well and is predictive and matches observations. However, quantum theory has no fundamental basis in nature. We're used to reductionist techniques. We went from molecules to atoms to protons and neutrons and electrons, and then we decomposed those even farther and found quarks. That's where everything stopped. Since then, we've been on this effective theory track, where neither general relativity nor quantum theory have a foundation, and they're also not unified.
Orton's Vicky observed that the motion of galaxy clusters didn't quite match what they expected from the calculations that they made. This data really looks consistent with missing matter that is not the ordinary stars that we expect to see. Around the 1970s, Vera Rubin came to the same conclusion, looking at a completely different scale, looking at spiral galaxies. In the 1970s, if you were a particle physicist, you would have dropped everything and thought about this problem.
One thing to note about spiral galaxies and Vera Rubin's observations is that she found the velocity of the stars and solar systems in the galaxy was faster than would normally be predicted for the amount of mass in the galaxy. Now, I think in the new era we'll find several mechanisms that could be responsible for this. One such mechanism is that the supermassive black hole is somehow emitting spacetime, possibly via the jets when the jets are active, but also possibly just emitting spacetime. It's so small and so non-interactive, it may just be able to escape right out of a black hole. Now remember, scientists look at photons when they determine what can escape out of a black hole, and they said photons can't escape. And that may be true. Photons are an assembly of point charges. Perhaps they're not formed at the edge of the black hole, or perhaps they truly can't get up enough velocity to get out. However, no scientist has ever considered whether point charge assemblies of space-time can escape a black hole. I believe they can. And they just may emit from the surface. There may be certain conditions required, like spin of the black hole. But if you consider that these black holes can emit space-time, and that space-time is extremely high energy at that point, you can imagine that those assemblies of space-time could interact. And simply their interaction could spin out standard model particles. Also, I don't know if you would call it the wind of new space-time, but that may have something to do with the overall velocity curve in a galaxy. If you can imagine, the central black hole is just constantly recycling matter that falls into new space-time. There's kind of this space-time being emitted that's kind of pushing the other space-time out of the way. And also, as that super hot space-time comes out of the supermassive black hole, it's going to inflate, and then it will expand from there. Those are some possible mechanisms that could explain the rotation curves that Vera Rubin saw.
Around this period of time, particle physics, which was a new field, were building new toys, these colliders where they're smashing together protons and producing all sorts of new and unexpected particles. And it was a puzzle. Why are we getting all of these particles? Where are they coming? Are they inside the atom? What does that mean? I will arbitrarily pick a period in the 1970s. So my high mark will be the Nobel Prize for what's called the electroweak theory. Benchmark for me for the development theoretically of what we now know as the standard model of particle physics. It was a heroic effort between experimental and theoretical physics to build this mathematical edifice. And there was one puzzle, and that puzzle had to do with the reason why we built the Large Hadron Collider, and that thing is called the Higgs boson. The apology then is, if we have known about missing matter for almost 100 years, why is it that we're talking about dark matter and the theoretical progress in dark matter in the 2010s, 2020s with fresh new eyes?
It turns out Flip's question has a direct answer. And the answer is that scientists missed the solution to nature over 100 years ago. And because their path deviated into the effective theories of general relativity and quantum mechanics, and then quantum theory, they are essentially lost. They have math and observations that match, they have predictability, but they really don't understand how nature works. And it's so amazingly beautiful and simple. And had they figured that out when they should have, which is around 1900, then we wouldn't have a Large Hadron Collider. We would have solved nature in the early 1900s and been much farther along.
If you ask me, the standard model looks like this. We've seen tables before. In chemistry, you have a periodic table. The periodic table is fantastic because the table is an organizing principle. If you have a box on the table, you know there's an atomic number, there's some number of protons, some number of neutrons, and this mathematical picture of what we call the standard model of particle physics. The periodic table reflects a deep mathematical organizing principle, and that is quantum mechanics applied to atoms. This thing is beautiful because this also reflects an organizing principle. This organizing principle lives within a generalization of quantum mechanics called quantum field theory. What this table is, each row is a class of particle, or a quantum field. 1/2 means these are matter particles. If it's not 1/2, it's a force particle. And each of these columns is one of the 3 fundamental forces of particle physics. So gravity is not included here. Each of these funny symbols is a mathematical description of how those particles interact under these fundamental forces.
This is probably a good time to mention that the standard model is entirely based on assemblies of point charges that make these different particles. When you have assemblies of point charges, there's no particular closed form mathematics that I can tell that describes these assemblies. They're always vulnerable to perturbation from other nearby assemblies or interaction with denser space-time near massy objects. They release energy in the form of redshift. And so the mathematics is built on top of shifting sands, in a sense, because there's really only point charges in the universe, and their movement, the path of each point charge, is described by a single evolution equation through the universe. And that is that every point charge in the universe is, at every instance, influenced by every other point charge in the universe, and sometimes by itself, if it's ahead of its own potential wave. So there's really only one equation in the universe. All other math is based on trying to describe assemblies of point charges and how they behave. This is a really interesting point because it has a lot to do with why things are so difficult to understand.
The one thing that was missing from the Standard Model of the 1970s was something related to the Higgs boson. It was this question that if we didn't have this last row, something funny happened to our equations when we calculated the likelihood for two particles smashed together. And the mathematics were giving us weird numbers like infinity. And the simplest explanation for why this theory would make sense is that there is one more line here, the Higgs boson, that had particular properties, and if you turned the crank, everything made sense.
The sea of space-time assemblies that permeate the universe have sort of a reusable, scalable architecture. The core element in nature is simply the binary of one negative point charge chasing a positive point charge around in a circle. Now, what happens at extremely high energy is that there's some form of capture of different energy binaries. And when they have different energy, they have different radii, and they have different frequency. So what I believe happens is that at vastly different scales, this capture occurs up to 3 binaries. And why 3? Because our space, the Euclidean space that's the background for the universe, is 3-dimensional. I call this triple nested binary a Noether core after Emmy Noether, because it really has a lot to do with the subjects she studied in her mathematics: conservation, momentum, and so forth. The Noether core can come in 2 different formulations. One of them we call the pro-Noether core, and that's used to make regular standard model particles. And the other configuration of the Noether core is used to make antiparticles. Each kind of Noether core can support 6 point charges in the polar regions, 2 per binary. And that's what gives standard model particles, at least the fermions, their personality. Now, what I think is happening here in terms of space-time is that I think Noether cores that are extremely high energy, that are extremely small, are just permeating everything. And I think they also may gently couple in the form of 2 pro-Noether cores and 2 anti-Noether cores, that they kind of just nestle up next to each other. A lot like the helium atom. And it turns out that that set of 2 pro-Noether cores and 2 anti-Noether cores yields 24 point charges, which is 6 per Noether core. It turns out 24 point charges is just the right amount to make a pro and an anti-fermion of any type. You've got a total of 12 negative point charges and 12 positive point charges in this nestled group. And you've got 2 pro-Noether cores and 2 anti-Noether cores. And so if there is a nearby reaction among other standard model particles, then the space-time particles can contribute. They may give point charges and energy to that reaction to produce other products of the reaction, or some of the products of the reaction may end up joining space-time. And that's really fascinating. It will explain a lot about how the universe works.
There is one additional puzzle. Why is it so light? We now know that the Higgs boson weighs about 125 times the mass of a proton. If you turn the crank in this theory, you would expect it to be much heavier. And so, if you zoom back to the 1990s, they had 2 choices. One choice was this puzzle of why is the Higgs boson light? Which one are you going to work on? Right? The one where there are faculty who will hire you as a postdoc. So this was the most important question.
This comment by Flip about the direction of science being directed by the positions offered as postdocs, which are set by hiring professors and department heads, in terms of their local strategy. The main problem here is that scientists have been banging their head on a very difficult approach to nature for 100 years. They made a lot of progress through the 1960s and early 70s, but for the last 50 years, there hasn't been much progress in fundamental particle physics at all. And because of not being on the correct ontology, everyone in these fields is totally confused. The narratives or the stories they tell about how they think nature works are just often wrong. That can all be corrected by going back in time to around 1900 and re-examining the assumptions that led us astray.
And now I'm going to lead us down to the story of the weakly interacting massive particle, the WIMP. And this dominated our idea of what dark matter ought to be for about 30 years. So you have this big problem. Why is the Higgs boson light? You do the calculations, it doesn't seem to make sense. But you realize that there's a way to explain why the Higgs boson would be light. And that's to invoke some deep, elegant mathematical principle that would explain why the theory is actually more constrained.
I find it rather surprising that scientists are looking for missing mass, and they don't really seem to consider that mass could be shielded. Because from Einstein, we know mass is energy, and energy is mass. They can be converted from one to the other. But we also have other concepts of how energy can be created. It can be differentials in potential. There can be superposition. There can be high frequency components that we can't even measure yet. There's just so many effects that could account for missing mass. And instead of kind of looking at these questions as evidence, they keep digging onto the really unproductive ground they've decided to try to mine. And this idea of a weakly interacting massive particle plays straight into that. They know it's massive, but they know they can't see it. So where could it be? And it would seem to me again that the ideas for where to find the WIMP or how to understand it would tend to look internally to the standard model particles, would tend to look for an implementation in space-time that would shield a lot of energy. But yet, none of this has jumped out, and I think it's because of the wrong turn on the ontology around 1900. And I think it must be that the math doesn't lend itself to this kind of creativity, that they believe the math is kind of locked in some places and doesn't yield itself to the kind of creativity required to kind of reverse course and find the solution at this point.
Supersymmetry is some deep, elegant mathematical relation between force particles and matter particles. An electron is a matter particle. There's a silly force particle called a selectron. So this ends up solving this puzzle. The symmetry, because every particle has a copy, gives you new particle. The moment you put these new particles in, and you knew exactly what they were, because there's a proton, there's a superproton, all this stuff, protons suddenly have new reactions where they can decay. The bound on the lifetime of the proton is actually longer than the age of the universe. You know, this is some weird practical problem. This elegant, deep mathematical thing was so beautiful. Let's try to save it. And what we do is we put a Band-Aid, a mathematical Band-Aid, and we invent some additional symmetry. Maybe there's some rule that prohibits these interactions. But what this R parity does, mathematically, the interactions that would have caused the protons to decay are no longer allowed. And it looks like everything starts to work again. You solve your deep, elegant problem, and the immediate other problem that comes up seems to be okay. What else does this theory do for us? Well, with all of these new particles and some reason, some parity, it turns out the lightest new particle is stable. So the reason why electrons don't decay into neutrinos is because electrons are the lightest particle that carry electric charge. There's no way to conserve charge if that electron decayed. So the lightest new particle, which carries our charge, is stable, cosmologically stable. And the one thing that we knew about dark matter is roughly how much there is. This calculation is telling you how much dark matter is left over after the Big Bang. So on the one side of the calculation, you're doing this particle physics calculation, something about quantum mechanics and reaction rates for producing dark matter and dark matter annihilating. On the other side of this calculation is something about the expansion of the universe to figure out how much dark matter is left over. So you have gravity, and on the other side, you have all these particle physics numbers. The number that comes out is the correct number. No, okay, that's a lie. But it was a correct number within a couple of orders of magnitude. There's one game that I know how to play, and it's this puzzle of why is the Higgs light? Oh, maybe we got it wrong last time. Okay, let's try alternatives. Let's look for some other deep, elegant mathematical explanation for why the Higgs mass should be light. And it turns out one such deep, elegant mathematical solution is to extend space-time, have an extra dimension. These extra dimensions predict new particles. Turns out these new particles, when you put them into your theory, screw up all sorts of weird observations that we found over the past 30 years. So you invent a humbler new symmetry. It's a band-aid, mathematical band-aid. It's called Kaluza-Klein parity. What that means is some of these new particles are prohibited from interacting in certain ways, and it ends up curing these observables, just like preventing the proton from decaying. The new particles that you get, they inherit their properties from the Higgs and all of the Higgs' cousins. Why? Because there is this deep, elegant mathematical symmetry. It's like a mirror. The thing on the other side of the mirror, you know what that person looks like. Why is the Higgs light? Let's think of a new reason. Maybe there's substructure. Maybe the Higgs is not a fundamental particle, but there are some, subprotons and subneutrons that come together to form the Higgs. Oh, okay, so what does that mean? Well, if you have like subprotons and subneutrons and you have some other particles, great. Is that okay? No, probably not, because you have all these observables that we have seen, and these new particles screw it all up. We can apply a band-aid. This one's called P-parity. What does it do? Well, it solves this problem, and it means that the lightest new particle is cosmologically stable. The details of this calculation, even though it's on the one side it's all particle physics, on the other side it's all general relativity, the fact that they're all the same essential properties, the same essential mass scales, the same essential fundamental couplings, if you're within a couple of orders of magnitude, it's going to land in that window. And as a discipline, you're feeling pretty darn good. Not only was there this puzzle where you needed a Higgs boson, okay, we predict the Higgs boson, but then you anticipated another problem, and you came up with this deep, elegant mathematical solution, not just one, but three. And each one of those predicts new particles. You tell your colleagues, we have to build the collider, we have to look for the Higgs, and then we will learn truth. There's something to see. If you didn't find the Higgs, that's even better. It's a bigger mystery.
Okay, I let that section run uninterrupted for a while. And what you saw there was Flip kind of going through the history of the attempts to mathematically solve these problems around the Higgs particle and around dark matter. And each attempt seemed to the physicist like it might work. Maybe there's weakly interacting massive particles. Maybe there's supersymmetry. But they would go down these paths and eventually get into a point where everything knotted up. There were roadblocks. And then they would invent additional math to repair the math they created to solve issues with how the Higgs works and how dark matter works. And again, this is all just a Sisyphean effort. It's impossible, I think, for them to solve it this way, because the answer is not going to be found based upon an ontology that is wrong, an ontology that is missing a fundamental understanding of even why that ontology partially works, or works so well, as some scientists might say. But it really doesn't. All of the measurements we do today and all the science is relatively low energy physics, even the Large Hadron Collider. If you think about the energies required to reach Planck scale or to actually reach the speed of light, like 0.99999 of the speed of light, that's a lot of energy. We're nowhere near that in our experiments.
The key point is when you have this no-lose theorem, that there is a deep, meaningful reason to build this collider because whatever comes out, you will learn truth.
So this is one of the syndromes in high energy particle physics, is that they feel like the path forward to learning more about nature is to go to higher energy colliders or colliders that use different fundamental particles such as muons. And it turns out nothing could be more wrong. What they are actually doing is accelerating standard model particles in opposite directions such that they reach very high speeds, somewhere close to the speed of light. But as I said, not really in terms of high energy. They then collide these particles. Surrounding all these particles is this soup of space-time assemblies, which permeates everything. And so when these two standard model particles collide and their assemblies degrade or break apart or have a reaction, they also can react with the space-time assemblies and create new particles. Because, if a proton has 36 point charges and you slam another proton into it with its 36 point charges, and each of those protons has 3 pro-Noether cores, and it's all permeated by space-time assemblies, which are pro and anti-Noether cores that have extremely high energy and are extremely well shielded. Well, you can create all kinds of different things flying out of that reaction that might look like a particle. They might kind of cluster together for a while in some form of stability before they degrade, or maybe they are stable particles that fly off out of that reaction. I'm not sure that with their ontology, continuing to smash things together is going to be helpful in terms of yielding new insights into nature. They may find some new things, but I don't think it's going to help them solve how nature works. I mean, as I've said, if you're on the wrong ontology, it's extremely hard to break through and figure out what's going on.
The key point is when you have this no-lose theorem, that there is a deep, meaningful reason to build this collider because whatever comes out, you will learn truth. And then even faster than it took to build this, you go from this to this, the Nobel Prize for the Higgs boson, 2013. And then remember the Nobel Prize for the discovery of supersymmetry, the Nobel Prize for the discovery of extra dimensions, the compositeness of no. Something went tremendously right. There was a Higgs boson, but something went tremendously wrong. So 2013 happened to be the year that I defended my thesis. Chapter 1 was supersymmetry. Chapter 2 was extra dimensions, and Chapter 3 was the compositeness of the Higgs, and all of the great new things we would discover at the Large Hadron Collider.
So here's Flip making kind of a gallows humor attempt at apologizing for all these efforts to explain what's going on. He names 3 here that just didn't pan out. They didn't win Nobel Prizes. They didn't become mainstream physics. And, that's certainly dismaying for the people in this field. I think that gets to why, Flip titled this talk An Apology, and why I see it kind of more as stages of grief of a person who came into the field very excited, was touted as possibly being able to make some breakthroughs, then struggled with his team on different potential ideas, and none of them panned out. I mean, that's got to be disheartening.
So for the past 2 years, the North American particle physics community goes through this decadal process where we review what are our priorities, our scientific priorities in our field of fundamental physics. And it should not surprise you that one of the unifying themes was to understand what is dark matter. So that says something about particle physics. That says something about where the field is.
Flip is mentioning here the prioritization process that physics use to lay out their strategic roadmap and justify funding. I did make a recent video about this. I will post a picture of the title slide for that video here. You can find it on my channel. But it's it's kind of a sad state of affairs, like what's happening in terms of funding. So much money goes into nonsensical subjects in the fields of physics and cosmology. They seem like they make sense to the current era scientists in terms of trying to figure out what's going on, but they are so lost that, it's all basically a lot of wasted money and effort.
What is the difference between these two pictures? One of these is the Millennium Falcon. I think this is a screenshot from one of the movies, so let me say this is the Millennium Falcon. The other is a Lego model of the Millennium Falcon. And there's something very deep here that I think it rings true to any physicist. The model is an approximation for the actual thing. If you zoom into the model, if you lift it up, if you look around, if you pick it up, you say, hey, this thing is kind of small to be the Millennium Falcon. In the right context, you learn something about the Millennium Falcon. There are things you can learn from a model, but the model is not nature. The fact that you have a mathematical model does not prescribe what ought to happen in nature.
Flip is making an important point here. The model is not nature. The map is not the territory. A Lego assembly that looks like a Millennium Falcon is not the Millennium Falcon. This is critically important to understand this, because if you trace back in general relativity or in quantum theory to the roots of those theories, at some point there's no model underneath it. It's just, here's the math. And we don't understand why this math appears to work as well as it does. We just don't know what's going on beyond that point. And so definitely it's true, the model is not nature, at least so far. And it's also true that the map is not the territory. And it's easy for scientists to get lost in believing in their own model so deeply that they actually think the model is nature, or they behave in the way they would if they thought the model was nature.
And this is where we are, this particle. Most of the particles that we know of are actually unstable. You have to explain, why is that particle still around? Given that we've been searching for dark matter for 30 years, then your theory has to say why we haven't found it yet. Any theory worth its weight will tell you, and this is how you will discover this type of particle. It'll give you something falsifiable. And so for the weakly interacting massive particle, there is some deep, elegant mathematical symmetry that explains to you what this new particle is. And that was very deep and exciting and meaningful. Then there's a series of answers of how did it get here? Well, the same way that ordinary particles got here, through something called thermal freeze-out. That was the calculation that we asked the grad student to do over and over and over again. Why is it still here? We had to put that Band-Aid on. Remember, if you put this Band-Aid on, you solve some problems, and for free, you get stable particles. Why isn't it ruled out? For all we know, dark matter might still be a WIMP. How do we discover it? For the WIMP, we keep doing exactly what we are doing because we have the experimental program to probe this. Maybe we start with, there is dark matter. Let's build the simplest building block, the simplest mathematical model, and see what comes out. How do you discover it? You start thinking more creatively, right? If there are different answers to how to get here, you have different interactions, which means there are different reasons why it's stable, and you have different ways in which it will manifest itself. There are a handful of black holes. So this is a quasar. There's a handful of these. These are galaxies far, far away that are powered by a supermassive black hole. What's the difference between a black hole and a supermassive black hole? The supermassive black hole is so large that our understanding of how black holes form cannot explain how they got so darn large. And the usual story is that First, you form stars, and stars form little black holes combine to form big black holes, but that cannot happen fast enough to explain these gigantic black holes. And one of the really cool things that we've been doing, this is a photo taken earlier today, has been puzzling over the ways in which the dark matter, which we know was already in these galaxies because they held the galaxy together.
So Flip here is talking about supermassive black holes and how did they form and get so large, and that the size is not consistent with the age of the universe as predicted by the lambda cold dark matter model, which says the age of the universe is about 13.8 billion years and that it originated in a big bang. So you see that LCDM has already had some tensions in it, and recently with the James Webb Space Telescope, more and more tensions are becoming apparent. And scientists are starting to really struggle to explain how things so far away in observations in terms of time and distance can be consistent with the Big Bang model. And it can't. Cosmologists totally misunderstand inflation and expansion. They think the overall universe is expanding, and they think that inflation is a period that happened right after a Big Bang. And they just don't understand that space-time is made out of point charge assemblies, and those assemblies are scalable. So when new, fresh, highly energetic space-time becomes emitted out of a black hole, becomes free in that sense, and starts spreading out and spreading energy to other space-time assemblies, those space-time assemblies, all of them will just inflate very rapidly, and eventually they will expand from there. And so inflation and expansion are galaxy local behaviors. All galaxies will, in essence, be competing with their galactic neighbors in terms of the space-time they emit. In between these galaxies, in deep space, there is some equilibrium that tends to be reached when massy objects are so far away that they have little effect on exciting the space-time. Well then, the space-time from this galaxy and the space-time from this galaxy, as they kind of meet over extremely large distances, those clouds of hotter space-time dissipating away from the massy galaxy will come to a minimum at some point of dissipated energy. And that's kind of the local minimum for space-time energy in that region between those galaxies. And then you just look at all galaxies. So you're going to have fluctuations in space-time energy all over the place because of this. And scientists have no clue about that right now.
Might be contributing to answering this puzzle. And there's an analogy that we often use. Dark matter isn't dark, it's invisible. Maybe the way that we have been doing things might not be the best way. Maybe there should be new approaches and new theoretical constructions, new frameworks to approach this puzzle. We can't afford to leave any great thinkers or any great ideas behind. The limiting factor is human. Why do we do this? There's a painting by Paul Gauguin. Who are we? Where do we come from? Where are we going? I think about this painting because it reminds me that every culture, for as long as humanity has been human, has had a story, has had a cosmology of how we belong, how we came to be who we are, where we came from. Right now, science is part of our cosmology as a global human species. And we have our own story. And that story is something like this. 13 billion years ago-ish, there was something called the Big Bang. We don't quite understand what happened. The Big Bang formed a lot of the matter and stuff in our universe.
This image that Flip is showing about the Big Bang is a classical image that is shown all the time to illustrate lambda CDM. And the interesting thing is the timelines and the phases are probably reasonably correct. It's just that that's happening in each galaxy around the supermassive black hole, and it's happening periodically when they emit space-time through the jets, or even continuously when they emit space-time just through the surface of the black hole.
A good chunk of that stuff is dark matter, which you see here in these weird filaments. The universe expanded rapidly and cooled down, and these filaments condensed. Where these filaments overlap, there's an overdensity of gravity. It started pulling in more dark matter. That dark matter overdensity then had a bigger gravitational pull and started pulling in this really funny stuff called hydrogen gas. And that hydrogen gas collected into this clump of dark matter, and eventually the hydrogen gas found each other, and they started forming these funny things called stars. Some of those stars would go supernova and produce metals, and you would form more complex stars. Those would get together into things called galaxies. In the galaxies, you find these little solar systems. There's a planet called Earth, and there are these people who are just discovering the dark matter ocean that we happen to be living in. And that is why we do this. So thank you very much.
So we've reached the end of this watch party. I thought Flip gave a reasonable talk that was representative of the state of particle physics and the search for information about the Higgs and a solution to dark matter. And I think he pretty much illustrated that it's a very confused field. They've tried many things, many ideas, a lot of math, a tremendous amount of work has gone into this. To get a breakthrough with just these mathematical approaches that treat nature as if it's just going to reveal itself with these complicated mathematics, it's just not going to happen. Thank you for watching, and I'll try to do more watch parties in the future. This was kind of fun. Bye.